So welcome back, everybody. Welcome to my fourth lecture on interpretations of quantum mechanics. In this fourth lecture, I want to talk in particular about relativistic aspects. Let me start with the Einstein-Podolsky-Rosen argument. So EPR wrote a paper in 1935 in which they gave an argument for the claim that there are additional variables beyond the wave function, hidden variables. Here's the argument in a version due to Bohm in 1951. Bohm in 1951 wrote a textbook on quantum mechanics. Consider two particles, spin 1/2 particles. They're space-like separated, but their spin state, now the position dependence is not of particular interest. Let's say the wave function factorized to spin state times the position dependence. And the spin state is the so-called singlet spin state. The name singlet just means, if you consider the representations of the rotation group, then they fall into a three-dimensional subspace and a one-dimensional subspace, and the one-dimensional subspace is called the singlet. Okay, so it's a particular spin state. I've written it down here, up, down, minus, down, up. Now, Alice measures sigma z of particle 1, obtains the outcome A. Now, A is not a self-adjoint operator. A, the notation means in the following, the outcome that Alice obtains. So it could be +1 with probability 1/2 or -1 with probability 1/2. And then the wave function collapses. If the outcome was +1, the wave function collapses to up, down. It was -1, it collapses to down, up. Then Bob measures sigma z on particle 2. So Alice and Bob are their labs are space-like separated, and particle 1 is in Alice's lab and particle 2 is in Bob's lab. Now, obviously, Bob obtains the outcome -A. Let me call the outcome B with probability 1. Now, from this, EPR conclude that particle 2 had a definite sigma z value already before Bob's measurement. Well, usually in most cases, any observable has a value only after you do the measurement. Okay, but since before the measurement, it was already clear with probability 1 what the outcome would be. In this case, it so happens that the sigma z of particle 2 had a definite value already before Bob did the measurement. Now, EPR makes the following assumption, a locality assumption. It says space-like separated events cannot influence each other. So that is something that you would think is true because of relativity. For sure, in classical theories, if you have space-like separated events, they can't influence each other. In particular, Alice's measurement cannot change the physical situation on Bob's side. Okay, so that's the locality assumption. Now, from that, it follows that Bob's particle number 2, had a definite sigma z value even before Alice's measurement. Why is that? Because before Bob's measurement, it had a definite value, but Alice's measurement didn't change anything about the state of affairs, the physical situation on Bob's side. Therefore, Bob's particle must have had a definite sigma z value already before Alice's measurement. Although the initial wave function psi is not an eigenstate of the observable that Bob measured. The observable is identity on particle 1 times sigma z on particle 2. Quod erat demonstrandum. So this is what EPR had claimed. So there are sometimes situations where there is a fact in nature about that doesn't follow from just the wave function alone. Okay, the wave function is a superposition of different values of sigma z for particle 2, but this reasoning yields that there must have been a fact in nature already before any measurement about what sigma z of particle 2 has been. Of course, you could run the same argument with Alice and Bob interchange. So also for particle 1, there must have been a definite value of what its sigma z actually is, even before anybody made any measurement. In their original 1935 paper, they gave the argument not in terms of spin, but in terms of position. Okay, so let me go through the argument again in terms of position. Okay, so the claim is, let me reiterate, there are additional variables beyond the wave function. So they consider 2 particles. Oh, no, it's not spin 1/2. That's a mistake on my slide. Spin 0 particles. Okay, in 1 dimension, with an entangled wave function of this form, a delta function of x1 minus x2 plus a constant. X0 is kind of something like the distance between the 2 particles, a large constant. Okay, let me draw a picture of that, what this wave function looks like. Where's my whiteboard? Okay, let's see. So here's the configuration space of the 2 particles, x1, x2. Good. Now, this delta function is concentrated on a straight line. Okay, so I didn't draw a perfect straight line. It's supposed to be a straight line at 45 degrees. That's where the delta function is concentrated. It's a delta function. Let me write it down here. Where am I? Delta function of x1 minus x2 plus x0. So x0 is what you see here. So here you have 45 degrees plus this offset of x0. So that is what the initial wave function looks like. Now Alice measures position. Okay, so she finds some value of position. Let me call that capital X1. So that's her outcome. Now the wave function has to collapse. It has to collapse on, on this subset of configuration space, which means it collapses to just this point here. Okay, so now it becomes a delta function in 2 variables. Let me show you that on this slide. Okay, here now it's a delta function on 2 variables. So the x1 variable is concentrated on the actual value, x1 that was found, and the x2 variable is concentrated on x1 plus x0. Okay, so the x1 was uniformly distributed. Well, okay, so the way EPR wrote it down, it's uniformly distributed over the whole real axis. Of course, there is no uniform distribution over the whole real axis, so say over some very long interval. Good. Now, Bob, at space-like separation from Alice, measures the position of particle 2. And now it's determined with probability 1 what the outcome must be. His outcome x2 must be x1 plus x0. That reflects the fact that now the wave function is a delta function in both variables. So the fact that Bob's outcome is determined with probability 1 means that particle 2 had a definite position already before Bob's measurement. Okay, EPR make the locality assumption. Space-like separated events cannot influence each other. In particular, Alice's measurement cannot change the physical situation on Bob's side. Now it follows that Bob's particle had a definite position even before Alice's measurement. Why is that? Because Alice's measurement cannot have changed anything about Bob's particle because it's space-like separated. Okay. And after Alice's measurement, Bob's particle has a definite position, even before Bob makes any experiment. So already before Alice's measurement, it must have had a definite position. So EPR concluded that in addition to wave functions, there must exist further variables that include this definite position. And that is what they wanted to prove. Okay, and it follows by this argument from the locality assumption. Then in their paper, EPR went on to consider momentum measurements and to argue that by measuring position on particle 1 and momentum on particle 2, you could know both the position and momentum of each particle. But that was actually a bad thing to do. It was a distraction. Most readers kind of then thought a lot about having accurate measurement of momentum and position at the same time, and how that's possible. For example, Bohr wrote a reply, but the reply actually replied only to the second part of this paper. So kind of people were distracted from the first part, which is the central claim, which is what I just presented to you. Our consideration that involves only position. Forget about momentum. No talk about momentum. No mention of momentum necessary. Okay. There's another aspect of the argument that often creates a certain difficulty, and that's because in quantum mechanics, we often practice not to think about physical reality, but to focus on observable predictions. We try to figure out, okay, what will be the probability distribution for Alice's outcomes and Bob's outcomes or other outcomes. Now, with this argument, you can't understand the argument unless you think about physical reality. The argument concerns what must be there in physical reality, even if nobody knows it and if nobody can find it out. So there's a situation in which Alice and Bob don't know what the actual positions are, but EPR argue that nature knows what the actual positions of the two particles are, even if nobody knows it. So EPR concluded that the wave function is not everything there is in nature. Now, the argument is actually too good to be true. Okay, so here's the deal. The argument is actually correct. The argument shows that locality implies the existence of hidden variables. Why is that too good to be true? I'll explain. Okay, consider again this singlet state, up, down, minus, down, up. You can verify mathematically that this is actually the same state as right, left, minus left, right. Or for any direction in three-dimensional space, A up, A down, minus A down, A up. Maybe up to a phase. Okay, so there could be a minus sign here somewhere, or a phase factor. Okay, but up to a phase, it's the same state actually. So you could make the same argument, not just with sigma z, but also with sigma x or sigma y, with sigma in any direction. So A dot sigma, that's the sigma in direction A. So since the argument yields that there exists a hidden variable, that the measurement outcomes are predetermined, for the z direction, the same argument gives you a hidden variable for any direction. Now, from the no hidden variables theorems, we've heard already that that can't be. So what does that mean? Since the argument is correct, it means that the assumption, the premise, locality, can't be right. And actually, it was John Bell who realized in 1964 that locality is actually not true and that one can prove it. Let me give an example first. What does it mean that locality fails? Here's an example in Bohmian mechanics. Bohmian mechanics is a non-local theory. So what does that mean that it's non-local? It means the velocity of particle number 1 depends on the position of particle number 2. Why is that? That's because in the equation of motion of Bohmian mechanics, the velocity of particle number 1 is determined by the equation of motion. So there's an expression on the right-hand side of the equation that gives you what the velocity is. And it depends on the gradient of the phase of the wave function evaluated at the actual configuration, that is, the actual positions of particle 1 and particle 2. Now, particle 2 could be arbitrarily far away. So consider this EPR pair, they're space-like separated. So particle 2 is so far away that you can't have any light signals traveling back and forth. But nevertheless, according to Bohmian mechanics, the velocity of particle 1 depends on the position of particle 2. And if Bob influences the position of particle 2 through his external magnetic fields, then this will also have an effect on the trajectory of particle number 1, or vice versa. So Alice's magnetic field changes the trajectory of particle 2, the particle on Bob's side. And it does not depend on the distance. This effect doesn't fall off with increasing distance. And this also corresponds to the fact that Bohmian mechanics doesn't contain hidden variables for spin components, as EPR would have predicted, as EPR concluded from locality. Okay, so as I mentioned already, Bell gave a general proof that locality is false. Here's the statement of Bell's non-locality theorem. Some predictions of quantum mechanics are incompatible with locality, regardless of which interpretation of quantum mechanics is used. Put differently, certain statistics of outcomes predicted by quantum mechanics are possible only if space-like separated events sometimes influence each other. These statistics were actually confirmed in experiment. I heard people say that the first convincing confirmation were the experiments of Alan Aspect in 1982. But experiments like these have been done lots of times. And people have argued about whether there's a loophole, then people have done better experiments that exclude also any loophole. Now, the proof of the theorem is based on the following lemma, some auxiliary statement, which says non-contextual hidden variables cannot reproduce the statistics predicted by quantum mechanics for certain experiments. Now, let me remind you of what the upshot was of EPR's argument, now formulated in the language appropriate here. It's that locality implies the existence of non-contextual hidden variables for all local observables. And now the structure of the argument is as follows. If you have the EPR conclusion, locality implies non-contextual hidden variables. Bell's lemma, non-contextual hidden variables conflict with quantum predictions. These quantum predictions have been confirmed in experiment. You get the result, locality must be wrong. Now I'll give you a proof of Bell's theorem. For this, well, I've already told you how this follows from the EPR argument and Bell's lemma. So all that remains to be done is to prove Bell's lemma. Okay, so here's a proof of that. Consider again the singlet state, a pair of particles, space-like separated, and their spin state is this thing. Good. Now consider the following experiment. Alice chooses an arbitrary direction represented by the unit vector A in 3 dimensions and measures the spin component in this direction on her particle. Bob independently chooses a direction in space and measures the spin observable in this direction. So when you repeat that over and over, then you can, in the end, select all the cases where Alice's direction was a particular one and Bob's direction was a particular one, and you can evaluate the statistics. Quantum mechanics makes the following predictions. Predicts probabilities for the 4 possible outcomes. Here, theta means the angle between these directions A and B. Okay, the 4 possible outcomes of the experiment are plus, 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 minus, minus, plus, and minus, minus. So say this is Alice's outcome and this is Bob's outcome here. Okay, so this is the prediction of quantum mechanics. The fact that you have theta divided by 2 has something to do with spin 1/2, because of spin 1/2, kind of it's half the angle that plays a role. You can easily see that if you add that these four numbers are all between 0 and 1. You can easily see that they add up to 1. You can easily see that the sum of every row is 1/2 here. So if you just look at Alice's result, it has probabilities 50-50. If you just look at Bob's result, it has probability 50-50 because also the sum of every column is 1/2. Okay, but when you bring together Alice's result and Bob's result, you can determine the frequencies with which you have plus plus or plus minus, etc. So you can check whether this table here is actually correct. And all experiments have found it to be correct. Good. Now, here is why this table is in conflict with locality. If you assume locality, then by EPR's argument, Alice and Bob's outcomes must be hidden variables. They're predetermined. So there are some values. Say V1A is the outcome that Alice will obtain on her particle number 1 if she chooses to measure spin in the A direction. So that would be the hidden variable of this self-adjoint operator here, the spin observable in A direction times identity for the second particle. Okay, likewise with Bob, his outcomes are predetermined. Now since nature doesn't know in advance what Alice and Bob will choose, these values will be predetermined for every direction. So nature knows, if locality is true, for every direction what the outcome will be. These variables must have values plus or minus 1. And because of the situation, if Alice and Bob happen to measure in the same direction, then Bob's outcome is always the opposite of Alice's outcome. That is represented through this equation here. Okay, now consider 3 directions between which Alice and Bob can choose. Okay, let me call them alpha, beta, gamma. So now consider the following events. So now we're talking about probabilities that certain events occur. The variable V1 alpha equals the variable V1 beta. That may or may not be the case. V1 beta may or may not equal V1 gamma. V1 gamma may or may not equal V1 alpha. But one of these 3 conditions must actually be the case because each of the variables can only assume the values plus or minus 1. So if you have 3 variables and each of them assumes only the values plus or minus 1, then 2 of the variables must be equal to each other. So these are actually these 3 statements here, that which 2 are equal to each other. So this event here must occur, so it has probability 1. But then it follows that the sum of the 3 individual probabilities must be at least the probability that one of these 3 occurs. Actually, the probability that one of the 3 occurs is the sum of the 3 probabilities minus the probability that several ones of them occur. Okay, so it follows from just probability theory that the sum of these 3 probabilities must be greater or equal 1. Now, if you take into account that V2 is just the negative of V1, so you replace the V1 beta by minus V2 beta, then this equality means that these 2 are unequal, okay, because V1 alpha is equal to minus V2 beta. Okay, so I can just rewrite, I do this with each of these expressions, I rewrite the condition. Now the quantum mechanical prediction for A not equal B, let me go to the previous slide. So A not equal B means these 2 terms together. That's cosine squared of theta over 2. Okay, now if you choose your 3 directions, alpha, beta, gamma, let's say alpha upwards and beta this way and gamma this way, they all have 120 degrees. Theta over 2 is 60 degrees, cosine of 60 degrees is 1/2, square of that is 1/4. So each of these three terms is 1/4. You add them together, you have 3/4, a contradiction. So that was the proof that locality is actually wrong, the proof of Bell's theorem. In the literature, you will sometimes find misrepresentations of Bell's theorem. It is sometimes reported that Bell proved local hidden variables impossible. That is actually true. He did prove local hidden variables impossible, but it misses the point. So that statement, local hidden variables, that's actually equivalent to non-contextual hidden variables. So that's actually the statement of Bell's lemma, not of Bell's theorem. Let me go back to Bell's theorem and Bell's lemma. Okay, so people who mix up the two read Bell's lemma and say, this is what Bell proved. He proved local hidden variables inconsistent with quantum mechanics. But what Bell actually proved was that any local theory is impossible, is inconsistent with quantum mechanics, that is, with the predictions of quantum mechanics or with the empirical facts. Well, in 1964, these empirical facts were not yet established. So at that time, it was a prediction. So the structure is like this. Here, quantum mechanics means just the predictions. That means, going back to the previous slide, this table here. Okay, so QM means just the assumption that this table is true, which has been confirmed experimentally. So EPR proved that if you have quantum predictions, this table, well, EPR only considered the case where A equals B. So that means where theta is equal to 0. If theta is equal to 0, then this is 0. This is 1/2. This is 1/2. And this is 0. This is what we used in the EPR argument. Okay, let me go down 2 slides. Okay, so EPR showed quantum mechanics and locality together imply some statement P, the existence of non-contextual hidden variables. Bell's lemma proves that quantum mechanics implies that P can't be true. Now, if you draw the logical conclusion, then actually it's irrelevant what the statement of P was. The conclusion is quantum mechanics implies that locality is wrong. It is also sometimes reported that Bell disproved local realism and that we can choose to abandon either locality or realism. We have 2 options, they say. So you can keep locality if you want to by abandoning realism. Now, different authors who say that have different things in mind what they mean by realism, and maybe some are not very clear about what they mean by realism. For example, one possibility is hidden variables. Okay, so I just explained. You see, if somebody misses the EPR argument and the role of the EPR argument in Bell's argument, okay, then they would think, okay, there's a second assumption, which is P. But actually, P was not assumed. It was concluded, it was inferred from locality by means of the EPR argument. Okay. Here's another reason why people sometimes think that that there is a second assumption, some assumption of realism, which could be abandoned, and that is in 1976, Bell developed a second proof, a different proof of Bell's theorem that avoids the EPR argument. That had something to do with making the argument robust against small errors. What if you have small experimental errors and cannot verify that in the EPR case, the probability of equal outcomes is exactly 0? Okay, so he had a different argument where he had some symbol lambda for the hidden variables, or actually for whichever variables represent the physical state of affairs. So if you have no hidden variables, then lambda would be just the wave function. But many readers thought lambda means the hidden variables. So many readers had the impression that Bell is making an assumption that you have hidden variables. And you could just as well drop this assumption, not make this assumption of having hidden variables, and then kind of the argument would not apply. But the argument does apply, because if you assume you have no hidden variables, it means lambda is nothing else but psi, whatever you think is real. If there are no hidden variables, maybe it's just the wave function. But then the same argument does go through, and you get in the end that locality must be false. So it's actually not true that you can choose to abandon either locality or realism. Actually, there is no alternative to abandoning locality. So in particular, Bell didn't make any assumption of Bohmian of hidden variables. So for example, Bohmian mechanics, which doesn't have hidden variables for the spin observables, Bell's proof applies equally to Bohmian mechanics. Bell's proof applies equally to GRW theory, which has no hidden variables at all. Also, many worlds is non-local. Well, the way Bell's proof is phrased, it doesn't directly apply to many worlds, because it talks about probabilities. And actually, some advocates of many worlds have argued that many worlds is local, but I disagree. It's actually non-local, and I'll show you why. Let's see. A few more remarks about non-locality. It may seem that non-locality conflicts with relativity, and this is the main motivation for people to think that locality should hold, and that the motivation to think that something must be wrong with Bell's proof of non-locality, but actually there's nothing wrong with the proof. And actually non-locality does not conflict with relativity, and I'll show you why. But first, let me say a few more things. Einstein had a somewhat similar argument earlier in 1927. It's in the literature, it's called Einstein's boxes argument. So here's the consideration. Say the wave function of a particle, now we're talking about a single particle, not two particle, is half in this box here and half in that box. And one box is in Paris and one box is in Tokyo. They're very far away, space-like separated. Now you apply detectors to both boxes at a particular time t in some Lorentz frame at space-like separation. One and only one detector clicks. That's the prediction of quantum mechanics, because we have one particle wave function here. If it is assumed that there was no fact about where the particle actually is before the detectors were applied, then this effect is non-local. Einstein used this argument against the Copenhagen camp. The argument actually shows that any collapse theory is non-local. So if you want to prove that GRW is non-local, you can do it more easily than with Bell's non-locality theorem. You can say, if before Alice's experiment, there was no fact about where the particle actually is. Then Alice does her experiment. Then if instantaneously Bob's probability of finding the particle jumps to either 0 or 1, depending on what Alice's outcome was, then that's a non-local effect. The only way to avoid this non-local effect is if there was a definite fact already before the measurements about what the outcome would be. That means about where the particle will be found. That would be the case in Bohmian mechanics. In Bohmian mechanics, the particle is either here or there. And so nothing non-local is going on in this experiment. Something non-local is going on in Bell's experiment, but not in Einstein's boxes experiment. So that was another argument by Einstein for assuming locality, for arguing that something must be wrong with the Copenhagen interpretation. Of course, now that we know that locality is actually wrong, then kind of the interest in Einstein's boxes argument is limited. Okay, now I have a few slides on why many worlds is non-local, but maybe I skip these slides and turn to more interesting topics. Oh, okay, so if you can ask me in the end if you want to see these slides. If you want to know why many worlds is non-local, ask me about it. Okay, now I've claimed that non-locality does not ruin relativity, but for sure there's it's not obvious how to combine non-locality and relativity. It would seem that non-locality makes it hard to come up with a relativistic theory. And in fact, it creates a difficulty for theories such as Bohmian mechanics or GW to be extended to relativistic spacetime, to come up with any version of these theories that are compatible with relativistic spacetime. Okay, I will first discuss Bohmian mechanics in relativistic spacetime, and afterwards GW in relativistic spacetime. Here's the situation about Bohmian mechanics in relativistic spacetime. If a preferred foliation means slicing of spacetime into space-like hypersurfaces, is permitted, this slicing is, the technical term is the time foliation, and I will denote it by script F. If that is granted, then there is a simple, convincing analog of Bohmian mechanics. So that depends then on this foliation F. So this was developed by De and co-authors in the 1990s. Without a time foliation, however, no version of Bohmian mechanics is known that would make predictions anywhere near quantum mechanics. And I personally have no hope that such a version can be found in the future, although it's not excluded. There is no proof that this is impossible, but I don't think it will happen. So that means Bohmian mechanics needs a preferred foliation, special surfaces that somehow that define a temporal order of space-like separated events. Usually in relativistic spacetime, space-like separated events don't have a temporal order. You don't know which one is first. It depends on the Lorentz frame. Now, if you assume that there is a preferred foliation, if you assume there's something out there in the world that defines these surfaces, that would define a temporal order. Now there's the question whether this could be admitted as relativistic. So we arrive at the question, what counts actually as relativistic? Now, it turns out that the usual idea of a relativistic theory, that's pretty clear for a local theory, but it's kind of not clear-cut what it should mean for a non-local theory to be relativistic. So it seems like there is no single property of a theory that could be regarded as being relativistic. There are kind of several relevant properties. One is Lorentz invariance. But so Lorentz invariance here, let me say what that would mean. It would mean any Lorentz transform of any solution is another solution. What does that mean, a solution of the theory? Think of Bohmian mechanics. You have an equation, the Schrödinger equation for the wave function. You have equation, the Bohm's equation of motion for the particles. Okay, so you can have a solution of that. So a solution would consist of n trajectories and a wave function. Okay, now you Lorentz transform. Okay, you get other trajectories in a different wave function. You ask, is that again a solution? Okay, what you would use as the Schrödinger equation is, of course, the Dirac equation or some other relativistic equation. Okay, now this property that any Lorentz transform of any solution is another solution, that actually can trivially be satisfied. You just take any set of trajectories, you apply all Lorentz transformations, and you claim, oh, that's my theory. That's my set of solutions. For example, the theory could be non-relativistic. And then closing your set of solutions under the action of Lorentz transformations means nothing but the equations of your theory hold in some Lorentz frame. And that doesn't exclude, for example, superluminal signaling. So it would just mean, oh, there's one frame in which it's possible to send signals instantaneously. Okay, so when you think of it, then just the set of solutions being closed under Lorentz transformations is too weak a property. It's necessary, but not sufficient for anybody's notion of being relativistic. Here's another property, commutation of the field operators. Usually field operators in quantum field theory at space-like separated points, they commute. Okay. That, again, seems not sufficient for being relativistic. You could have a Bohmian theory with a preferred foliation, and still your field operators would commute. Think of Bell's non-locality proof. The operators, they commute. Alice's operator acts just on particle 1. Bob's operator acts just on particle 2. They commute trivially. Okay, so that doesn't, that by itself doesn't make the theory relativistic. You would demand that there's no signaling faster than light. Again, that's necessary but not sufficient. Some authors have tried to write down what it means for a theory to be relativistic, and what they've written down is equivalent to locality as discussed by EPR and Bell. Now we know that can't be true because that's violated in nature, so a theory cannot satisfy that. Then you might ask that there is no additional structure. You're not allowed to introduce a foliation. The only things that you can use are the space-time metric, which perhaps is curved, and the wave function. However, that's not very clear-cut either, because you could define a foliation from the space-time metric or the wave function. I'll show you an example on the next slide. Another property that people have discussed is microscopic parameter independence. Okay, some name, here's what the property means. If two regions A and B are space-like separated in space-time, they're space-time regions, then the probability distribution of the primitive ontology in A, the world lines, the particle trajectories, or the flashes, or the matter density, does not depend on the external fields in region B. If the hidden variables, if there are hidden variables, are given and the external fields in region A, then it's unnecessary to specify in addition the external fields in region B. They don't depend on the distribution in region B. This is true in relativistic GRW theory, but it's false in Bohmian mechanics based on a preferred foliation. Essentially, it will depend on fields up to the same leaf of the foliation, that is, up to the same surface. Okay, so that's a certain property that Bohmian mechanics fails to have and that GRW theory has. So it seems fair to say that GRW theory is or can be made more relativistic than Bohmian mechanics. Still, let me dwell for a moment on the situation in Bohmian mechanics. So what we just discussed is kind of a semantic question. Semantic means what you mean by certain words, like what you mean by relativistic. But perhaps it's not so useful to discuss about what we should mean by certain words. The question is, could it be like that in nature? And to me, the possibility seems worth considering that our universe has a time foliation. And that's partly because the space-time metric itself might provide such a foliation. So here's the simplest choice of a foliation. The surfaces of the foliation, the kind of surfaces of simultaneity at a distance, are the level sets of the absolute time function, where the absolute time function, capital T, is the time-like distance of any space-time points, space-time point from the Big Bang. For example, here now, the time-like distance from the Big Bang is 13.7 billion years. That means the Big Bang was 13.7 billion years ago. In other words, you draw the surfaces that are sort of parallel to the Big Bang, the surfaces of constant, of equal distance from the Big Bang. Okay, so there are these, in this drawing here, they're the horizontal surfaces. Okay, so you see what this means is if you have a curved spacetime, and if your curved spacetime has an initial singularity, a Big Bang, then it automatically comes with a preferred foliation. There are preferred foliations in nature. The spacetime is actually not Lorentz invariant. Special relativity is Lorentz invariant, but general relativity is not. General relativity usually has few or no symmetries at all. The Lorentz transformations are a symmetry of spacetime, but if you have curved spacetime in general relativity, then spacetime is no longer symmetric. It has little ripples and little dents everywhere. So nothing is exactly symmetric. Okay, it comes with that, that in general relativity, you don't actually have Lorentz symmetry, and you have a preferred foliation. So considering that, it doesn't seem so bad anymore that you're using a preferred foliation in Bohmian mechanics. It could simply be this foliation that you're given anyway from the metric. Alternatively, you could define a preferred foliation from the psi, from the quantum state vector. You see, for example, in order to define a foliation, it's sufficient to have some scalar function on spacetime. Then the level sets of your scalar function will be three-dimensional surfaces in spacetime. Good. So now a wave function is not exactly a function on spacetime because you have many particles, more complicated than that. But usually you can do some mathematical operations to extract surfaces from the quantum state vector. This is discussed in this paper here. Or you could get a foliation by means of a Lorentz invariant law starting from an initial surface. Okay, so what I'm saying, the upshot of all this is maybe in the end, it's not so terrible to have a preferred foliation. Maybe it's a possibility worth considering. And now on the next slide, I will briefly explain how to do Bohmian mechanics once you have a preferred foliation. And after that, I will show you how GRW could do it without a preferred foliation. But before that, let's have a short break